There is a boundary to our solar system that no spacecraft has ever crossed. Not the orbit of Neptune, though Neptune is so far from the Sun that sunlight takes more than 4 hours to reach it, heliopause. Not the heliopause, the region where the Sun's stellar wind fades and the interstellar medium begins, which the Voyager spacecraft crossed after more than 3 decades of travel. Even the vast loneliness that lies space beyond Neptune, scattered with icy worlds and the remnants of planetary formation. There is something further, something so vast, so ancient, and so difficult to see that for most of human history it was simply unknown, inferred, theorized, suspected, but never directly observed. A structure so large that it would take the fastest spacecraft ever launched by human beings approximately 30,000 years to cross it. It is called the Oort Cloud, and it surrounds our solar system like an enormous, nearly spherical shell of frozen worlds, trillions of icy bodies, each one a traveller from the solar system's earliest history, drifting in the cold and dark at distances so vast that the Sun itself, brilliant star around which 8 planets and countless smaller bodies orbit, appears from the Oort Cloud as nothing more than a particularly bright star, slightly brighter than its stellar neighbours. Not the dominant, burning presence we know from Earth's sky. Just another point of light in an indifferent sky. The Oort Cloud is the solar system's outer edge, its farthest frontier, its oldest archive, and tonight we are going to explore it. We will travel outward from Earth, past the familiar planets, past the asteroid belt, past Jupiter and Saturn and Uranus and Neptune, past the Kuiper Belt and the heliopause and the vast middle distance of the inner Oort Cloud until we arrive at the outer reaches of the cloud itself, where the Sun's gravity barely holds these ancient travellers in their long, slow orbits. We have the whole night ahead. There is no hurry. The Oort Cloud has been waiting for 4.5 billion years. It can wait a little longer. And as we begin our journey outward tonight let us first establish the solar system we are familiar with, the one that fills textbooks and classroom diagrams, and understand why it represents only a small fraction of the full solar system. Familiar solar system, the one depicted in those diagrams, with the Sun at the centre and the 8 planets arrayed around it in their nearly circular orbits, fits within a region of space approximately 60 astronomical units across. And one astronomical unit, as we have discussed in other explorations, is the average distance from the Earth to the Sun, approximately 150 million kilometers. Neptune, the outermost major planet, orbits at approximately 30 ASTU from the Sun. 30 ASTU, 30 times the Earth-Sun distance. That sounds large, and by any terrestrial standard, it is incomprehensible. The distance from Earth to Neptune at its closest is approximately 4.3 billion kilometers. Fun. A journey at the speed of Voyager 2, the spacecraft that flew past Neptune in 1989, travelling at approximately 15 kilometers per second, would take approximately 12 years. But 30 ASTU Utes in the context of the full solar system, is almost nothing. Beyond Neptune lies the Kuiper Belt, a disk of icy bodies extending from approximately 30 astromuoti to perhaps 50 astromuoti from the Sun. Pluto is the most famous Kuiper Belt object, orbiting the Sun at an average distance of about 39 UKUts. Kuiper Belt contains tens of thousands of objects larger than 100 kilometers across, and potentially hundreds of thousands of smaller bodies. Beyond the Kuiper Belt, there is a transitional region, sometimes called the scattered disk, extending perhaps to 100 or 200 UKUts, containing objects that have been gravitationally scattered by the giant planets into highly elliptical inclined orbits. And then, beyond all of this, beyond the scattered disk, beyond the heliopause, beyond the 200 UKU that marks the practical limit of most solar system discussions, there is the Oort Cloud, beginning in its inner regions at approximately 2,000 ASU from the Sun, and extending in its outer reaches to perhaps 100,000 ASU cloud. Let us sit carefully with the numbers that describe the Oort Cloud, not to overwhelm, but to genuinely appreciate what they mean. Outer boundary of the Oort Cloud is estimated to lie at approximately 100,000 ASU from the Sun. 100,000 astronomical units, deep, 100,000 times the distance from the Earth to the Sun. Let us try to make that tangible. If the distance from the Earth to the Sun were represented as 1 centimeter, about the width of a fingernail, then the outer edge of the Oort Cloud would be approximately 1 kilometer away. 1 kilometer to represent the full extent of the solar system. The familiar planets on this scale would all be clustered within the first 3 millimeters, less than a quarter of an inch from your fingertip. Or consider it in light travel time. Light from the Sun reaches Earth in approximately 8 minutes. It reaches Neptune in approximately 4 hours. The inner edge of the Oort Cloud, at roughly 2,000 ASU, is approximately 11 light days away. The outer edge of the Oort Cloud is approximately 1.6 light years away. 1.6 light years. The distance that light, traveling at 300,000 kilometers per second, takes 1.6 years to cover. The nearest star to our Sun, Proxima Centauri, is approximately 4.2 light years away. The Oort Cloud extends roughly a third to halfway to the nearest star. The solar system does not end at Neptune, or at the Kuiper Belt, or even at the heliopause. The solar system, in its full extent, reaches nearly halfway to the nearest star, and in that enormous outer shell, that thin, cold, dark region between the planet we know and the stellar neighborhood we cannot reach, there drifts an estimated trillion to several trillion icy bodies, each one a remnant from the solar system's birth, each one older than any landscape on Earth, a trillion worlds in the dark, patient and cold and unknown, canned. As we continue our journey, let us explore how the Oort Cloud was discovered. Not through direct observation, because it has never been directly observed, but through the careful analysis of a phenomenon that has been puzzling astronomers for centuries. Comets have been observed since antiquity. These visitors to the inner solar system, visible as fuzzy, extended objects with long, bright tails when they approach the sun, have been recorded in astronomical catalogues from ancient China, Babylonia, and Greece. For most of human history, they were objects of mystery and often of fear. Harbingers of disaster, supernatural messengers, disruptions of the celestial order. By the 17th century, it was understood that comets were astronomical objects following orbits around the sun, subject to the same gravitational laws as planets. Edmund Halley demonstrated in 1705 that the comets observed in 1607 and 1682 were the same object returning to the inner solar system at approximately 76-year intervals. The comet that now bears his name. But Halley's comet and the other short-period comets, those that complete their orbits in less than 200 years, represented only one category of cometary visitor. There was another category, the long-period comets, those whose orbital periods extended to thousands or even millions of years. These comets arrived from seemingly random directions in the sky, not concentrated in the plane of the solar system where the planets orbit, but coming from all directions, as if from a spherically distributed reservoir. Where did they come from? What was their source? Gadin. In 1950, Dutch astronomer Jan Hendrik Oort published a landmark paper that addressed this question with a combination of careful analysis and elegant reasoning. And Oort examined the orbital parameters of a sample of long-period comets, specifically the quantity that describes the size of a comet's orbit, called the semi-major axis. What he found was striking. Many long-period comets had aphelia, their farthest sont point from the Sun, at distances of approximately 20,000 to 100,000 ASU, and they came from random directions in the sky. Oort concluded that there must be a vast spherical cloud of cometary bodies at those distances, a reservoir from which long-period comets were occasionally perturbed into orbits that brought them to the inner solar system. Cloud, he proposed, the cloud that now bears his name, was the source of the long-period comets. It was a profound insight. Thought inferred the existence of a vast and distant structure from the trajectories of its occasional wandering ambassadors. 10. Let us explore a refinement of the Oort Cloud picture that has emerged in subsequent decades. The recognition that the cloud is not a single, uniform structure, but contains distinct inner and outer components with different properties and different histories. Outer Oort Cloud. The region Oort himself proposed, extending from roughly 20,000 to 100,000 ASU, is approximately spherical. Objects in this region are so far from the Sun and the planets that their orbits have been randomized by the gravitational influences of passing stars and the tidal force of the Milky Way galaxy itself. Their orbital interpolations range across all directions, which is why the long-period comets they occasionally send inward arrive from random directions in the sky. but there is also an inner component, sometimes called the Hills Cloud, after astronomer Jack Hills, who proposed its existence in 1981. The Hills Cloud is thought to occupy the region from approximately 2,000 to 20,000 EU. It contains, by some estimates, far more objects than the outer Oort Cloud, perhaps several times as many. Its structure is less perfectly spherical, retaining more of the disk-like geometry of the original protoplanetary disk from which it formed, because objects at these distances have been less thoroughly gravitationally randomized. But the distinction matters for understanding where comets come from. Objects in the inner Hills Cloud are more tightly bound to the Sun and require a larger perturbation to be sent into the inner solar system. But they are also more numerous, and their reservoir is thought to be a significant source of comets on longer timescales. The two-component structure of the Oort Cloud reflects the different histories of its inner and outer regions. The outer cloud, shaped by billions of years of external gravitational influence. The inner cloud retaining more memory of its origins. Together, they represent the most complete picture we have of the solar system's cometary reservoir, a picture assembled not from direct observation of the cloud itself, but from the orbital evidence of the comets it sends visiting. As we continue our exploration, let us trace the formation of the Oort Cloud back to its origins, the turbulent early history of the solar system. Approximately 4.5 billion years ago, the solar system formed from a rotating cloud of gas and dust, the solar nebula that collapsed under its own gravity. As the central mass grew dense and hot enough to ignite nuclear fusion, the Sun was born, and the remaining gas and dust flattened into a rotating disk, the protoplanetary disk, from which the planets formed through accretion. Solid particles collided and stuck together, growing from dust grains to pebbles to boulders to planetesimals to eventually the planets themselves. The outer solar system, the region beyond the rocky inner planets, was a realm of ice, water, ammonia, methane, and other volatile compounds, too cold to exist as gas at those distances, formed solid ice crystals that became incorporated into the planetesimals forming there. The giant planets, Jupiter and Saturn, followed by Uranus and Neptune, grew from these icy seeds, accumulating gas and solid material until they became the enormous bodies we know today. But the formation of Jupiter and Saturn in particular was a violent and disruptive process for the rest of the outer solar system. Their enormous gravity scattered the smaller planetesimals that formed in their vicinity, sending them on highly elliptical orbits, flinging some into the inner solar system, ejecting others mystery, tossing others entirely from the solar system, and tossing many into the distant outer reaches that would become the Oort Cloud. This gravitational scattering is the primary mechanism by which the Oort Cloud formed. The icy bodies that now inhabit the cloud are not primordial objects that formed in situ at those distances, formed in the region of the giant planets, but approximately 5 and 30 Astromuitsi, and were then scattered outward by gravitational interactions with those planets, particularly T, Jupiter, and the objects scattered to the greatest distances, to tens of thousands of AU scans, were then further processed by external gravitational influences that rounded out their orbits from highly elongated to more nearly circular, populating the spherical outer Oort cloud. The Oort cloud is, in this sense, the debris of planetary formation, the icy remnants of a construction project that left its offcuts scattered across the outermost regions of the solar system. Let us explore one of the most remarkable aspects of Oort cloud dynamics, the role played by forces that are not planetary at all, but galactic, at distances of tens of thousands of AU. The gravitational influence of the Sun is attenuated to the point where other forces that are entirely negligible in the inner solar system, become significant. The most important of these is the tidal force of the Milky Way galaxy. The Milky Way is a vast disk of stars, gas, and dark matter, and our solar system is embedded within it, just as the moon's gravity raises tides in Earth's oceans, distorting the shape of the ocean in response to the gradient of the moon's gravitational field. The Milky Way's gravitational field exerts a tidal force on the Oort cloud. This galactic tide preferentially pulls on Oort cloud objects in the direction perpendicular to the galactic plane, slightly distorting their orbits over millions of years. For objects in the inner Oort cloud, this galactic tidal force is too weak to have much effect. But for objects in the outer Oort cloud, at distances of tens of thousands to 100,000 ASTU-UUs, the galactic tide is a significant perturbing force. Over millions of years, it slowly changes the orbital inclinations and orientations of outer Oort cloud objects, and can shift the perihelia of their orbits, bringing them from orbits entirely in the outer cloud to orbits that dip into the inner solar system, turning them into long-period comets. The galactic tide is, in this sense, a comet-generating mechanism. By slowly torquing the orbits of outer Oort cloud objects, it continuously delivers new cometary visitors to the inner solar system. There's something quietly profound about this. Comets that appear in Earth's sky, those ancient, ice-rich visitors whose tails stream for millions of kilometers as they approach the Sun, are not simply random objects from the outer solar system. They are, in part, objects whose orbits have been shaped by the gravity of the entire Milky Way galaxy, carrying the gravitational signature of the larger structure in which our solar system is embedded. A comet in Earth's sky is a message from the galaxy. As we continue our journey outward, let us consider what the Oort cloud actually contains, because the objects drifting in that vast outer shell are more than simply light icy balls of frozen gas. The estimated population of the Oort cloud ranges from approximately 1 trillion to several trillion objects, with diameters larger than 1 kilometer. Total mass of the cloud, uncertain by a factor of several, is estimated and at somewhere between 1 and several Earth masses. This mass, distributed across trillions of individual bodies, gives each body a relatively modest size on average. But the larger members of the Oort cloud are not small. Objects, tens to hundreds of kilometers across, are thought to exist throughout the cloud. Bodies, comparable in size to the largest objects in the Kuiper Belt or to the nuclei of the great comets that occasionally make their way to the inner solar system. These objects are composed primarily of ice, water ice, carbon monoxide ice, carbon dioxide ice, methane ice, ammonia ice, mixed with rock and dust in proportions that vary from object to object, are the most pristine preserved material in the solar system. At the extreme cold of Oort Cloud distances, temperatures approaching just a few degrees above absolute zero, chemical processes are essentially frozen. Material in these bodies has barely changed since the early solar system. They are time capsules frozen 4.5 billion years ago. When an Oort cloud object is perturbed into an orbit that brings it to the inner solar system for the first time, it carries within it a sample of the primordial solar nebula, the original material from which the entire solar system formed. The water, carbon and nitrogen in a long-period comet's nucleus have been sitting frozen in the Oort cloud since before the Earth existed. When a newly arrived long-period comet approaches the Sun and begins to sublimate, releasing its frozen gases and dust in the brilliant display of a cometary coma and tail, it is, in a sense, defrosting 4.5 billion years of preserved history. Let us follow a comet from its long sleep in the Oort cloud to its dramatic arrival in the inner solar system. Because this journey is one of the most extraordinary natural processes in our cosmic neighborhood. An Oort cloud object spends most of its existence drifting in the cold and dark at enormous distances from the Sun. Its orbit, if it has wings at all in the traditional sense, might take millions of years to complete. Its surface temperature is perhaps 5 to 10 degrees above absolute zero. Nothing happens to it. No geological activity, no chemical reactions, no significant change for millions or billions of years. Then something perturbs it. Passing star, one of the approximately 10 stars that pass within 1 or 2 light years of the Sun every million years or so, shifts its orbit slightly, or the galactic tide slowly torques its trajectory over millions of years. Hot, or a massive molecular cloud encountered by the solar system during its long orbit around the Milky Way center, adds its gravitational influence. The perturbation changes the comet's perihelion, the point of its orbit closest to the Sun. Instead of a perihelion in the depths of the Oort cloud, the comet's orbit now dips inward, perhaps into the inner Oort cloud region, perhaps over subsequent orbits, all the way into the planetary region. As the comet approaches the Sun for the first time, a journey that might take millions of years from its initial perturbation. So it passes through the outer solar system largely unchanged. But it approaches within a few AU of the Sun, the temperature begins to rise. the ices in its nucleus begin to sublimate, converting directly from solid to gas. The released gases expand outward, carrying with them dust embedded in the ice. Around the nucleus, a vast tenuous cloud of gas and dust. The coma forms, stretched by the radiation pressure and the solar wind. A tail develops, sometimes extending for tens of millions of kilometers, always pointing away from the sun, regardless of the comet's direction of travel. A long period comet from the Oort Cloud making its first approach to the inner solar system is among the brightest and most spectacular of all cometary visitors. Fresh, volatile rich material sublimating for the first time in billions of years produces an outgassing activity that well-travelled short period comets, which have been repeatedly baked by close solar passes, cannot match. These are the great comets of history, the visitors that appear unexpectedly, blaze brilliantly for weeks or months, and then recede back into the darkness, either ejected from the solar system entirely or beginning another million-year orbit back to the Oort Cloud. As we continue our exploration tonight, let us consider how the Oort Cloud is connected to Earth's own history, because the comets it sends into the inner solar system have over geological timescales been a significant factor in shaping the conditions on our planet. Delivery rate of comets from the Oort Cloud to the inner solar system is not constant. It varies over time, driven by the varying external perturbations that stir the cloud. Howled. When the solar system's orbit around the center of the Milky Way carries it through the denser regions of the galactic disk, the spiral arms, or the regions of higher stellar density near the galactic midplane, the rate of stellar encounters increases, and the galactic tidal force varies, and these variations perturb the Oort Cloud more strongly, increasing the rate at which objects are sent into the inner solar system. Some researchers have proposed that periodic increases in the cometary impact rate on Earth, sometimes called comet showers, could be correlated with periodic mass extinction events in the fossil record. The solar system oscillates above and below the galactic plane on a timescale of roughly 30 to 40 million years. This oscillation, some have argued, brings the solar system periodically closer to the denser regions of the galactic disk, increasing the stellar encounter rate and triggering comet showers. How deep? The connection between galactic dynamics and terrestrial extinctions remains scientifically controversial. The evidence is suggestive but not conclusive, and the periodicity claimed in the extinction record is debated. But the broader principle that the Oort Cloud connects Earth's geological history to the dynamics of the Milky Way galaxy is genuinely remarkable and genuinely supported by the physics. Earth's history is not merely a story of terrestrial geology and biology. It is a story embedded in the larger story of the solar system's journey through the galaxy, and the comets that journey delivers to our inner solar system are the most visible manifestation of that embedding. Consider one of the most profound connections between the Oort Cloud and the Earth we inhabit. The possibility that the water in our oceans arrived, in part, from the cometary reservoir of the outer solar system. Thought Earth formed in the inner solar system, in the region where temperatures were too high for water ice to exist as a solid during planetary formation. The early Earth was a dry, rocky body. The water, that now covers 71% of Earth's surface. The water in the oceans, in the ice caps, in the atmosphere, in the bodies of every living thing, had to arrive from somewhere. Two primary sources have been proposed. The first is water-bearing asteroids, rocky bodies from the asteroid belt that contain hydrated silicate minerals and carry water bound into their rock.
These asteroids could have delivered water to early Earth through impacts during the period called the Late Heavy Bombardment, approximately 3.8 to 4 billion years ago, when the orbital dynamics of the giant planets sent a barrage of impactors into the inner solar system.
The second proposed source is comets, icy bodies from the outer solar system that are essentially frozen water mixed with rock and organics. Cometary impacts in the solar system could have delivered substantial quantities of water directly. Distinguishing between these sources requires measuring the isotopic composition of the water. Water molecules in different populations of solar system objects have different ratios of deuterium, heavy hydrogen, to ordinary hydrogen. This ratio, called DHE, or the deuterium to hydrogen ratio, is a fingerprint of where and how water formed. Measurements of cometary water from multiple missions, including the Rosetta spacecraft's in-depth analysis of Comet 67P Churyumov-Gerasimenko, have shown that Oort Cloud comets generally have DH ratios that are approximately 2 to 3 times higher than Earth's ocean water. This suggests that long-perioded Oort Cloud comets were not the primary source of Earth's water, though they may have contributed some fraction. But the question is not fully settled. The measured comets represent a small sample of a population that spans trillions of objects. Possibility some fraction of Earth's water arrived from the Oort Cloud, from the frozen outer reaches of the solar system, remains alive in the scientific literature. Water you drink tonight may carry in its hydrogen atoms the signature of the outer solar system, Taman. And as we continue our journey, let us follow the furthest travelled objects ever launched by human civilization, the Voyager spacecraft, and understand what their journey tells us about the outer solar system and the approach to the Oort Cloud. Voyager 1 and Voyager 2 were launched in 1977, within weeks of each other. Their primary mission was to conduct flybys of the outer planets, Jupiter, Saturn, and in Voyager 2's case, Uranus and Neptune. They accomplished this mission brilliantly, returning the first detailed images of these distant worlds and their moons and rings. But the Voyager spacecraft were given a trajectory that did not return them to Earth. After completing their planetary flybys, they continued outward, and they have been travelling outward ever since. Voyager 1 is currently as of the mid-2020s, approximately 23 to 24 billion kilometers from the Sun, roughly 150 astrominutes. Voyager 2 is slightly closer, at approximately 19 to 20 billion kilometers. They are the most distant human-made objects in existence. And in 2012, Voyager 1 crossed the heliopause, the boundary where the Sun's stellar wind gives way to the interstellar medium. Voyager 2 crossed it in 2018. Both spacecraft are now, in the technical sense, in interstellar space. But they have not reached the Oort Cloud. They will not reach the inner boundary of the Oort Cloud. At approximately 2000 AUU, for another 300 to 400 years. They will not reach the outer boundary for approximately 30,000 years. And Voyager 1, the fastest moving human object ever created, travelling at approximately 17 kilometers per second, will take 30,000 years to cross the Oort Cloud, the familiar solar system, the one with planets and moons and asteroids, and the heliosphere, ends at about 100 AUU, full solar system. The one that includes the Oort Cloud extends 1,000 times farther. We are barely across the threshold. Let us explore the vast distance between the planetary solar system and the inner Oort Cloud, a region of space that is in itself extraordinary, despite receiving far less attention than either the familiar inner solar system or the distant Oort Cloud. Between approximately 50 ASTROMU and 2000 ASTROMU lies a largely unexplored region, sometimes called the inner Oort Cloud or the Hills Cloud, in its innermost portion, and simply the extended scattered disk in the region closer to the Kuiper Belt. This region is not empty. It contains numerous objects, some of which have been discovered through careful observation from Earth. Sedna is perhaps the most famous resident of this intermediate region, discovered in 2003, and Sedna has a highly elliptical orbit that takes it from a perihelion of approximately 76 astrominutes to an aphelion of approximately 937 astrominutes, well into the inner Oort Cloud region, patch, with an orbital period of approximately 11,000 years. Sedna completes one orbit during a span of time longer than all of recorded human civilization. Sedna's orbit is anomalous. Its perihelion is too large to have been produced by interactions with the known giant planets. It never comes close enough to Neptune for Neptune's gravity to have placed it on its current orbit. Something else must have produced Sedna's orbit, perhaps a stellar encounter during the early solar system, or perhaps the gravitational influence of a larger, undiscovered body in the outer solar system. Discovery of Sedna and several similar objects has opened a new field of planetary science, the study of the trans-Neptunian extended scattered disk and inner Oort Cloud, a region whose population and structure are only beginning to be characterized. Each new object discovered in this vast middle distance adds a data point to a picture that is still largely blank, a canvas stretched across hundreds of AU, on which we have managed to place only a handful of pinpricks of observation. We continue our exploration tonight, let us be honest about the remarkable extent of what we do not know about the Oort Cloud, because the genuinely unknown is as important to appreciate as what we have managed to learn. Again, the Oort Cloud has never been directly observed. Not in a single object has been confirmed to reside in the outer Oort Cloud through direct detection. And every piece of evidence for the cloud's existence is indirect, inferred from the orbital properties of long-period comets, from theoretical models of solar system formation, and from the physical necessity, the necessity of a reservoir to supply the observed cometary flux. This is a remarkable situation. We are discussing a structure that, by mass, likely rivals the Kuiper Belt or the asteroid belt combined. A structure containing trillions of objects, a structure that surrounds our entire solar system like a vast, tenuous halo. And we have never seen any of it directly. The reason is simple but frustrating. Oort Cloud objects are extraordinarily far away and extraordinarily faint. Distances of 10,000 to 100,000. Even a 100-kilometer wide body reflects essentially no sunlight detectable by current telescopes. The reflected light from an Oort Cloud object at 100,000 as UU would be approximately 25 billion times fainter than the reflected light from the same object at 1 AU. Next generation survey telescopes, particularly the Vera-C Room Observatory, which began operations in the mid-2020 and will conduct the legacy survey of space and time, will dramatically expand the catalogue of trans-Neptunian objects and may detect objects in the inner Oort Cloud. But the outer Oort Cloud will likely remain beyond direct detection for the foreseeable future. Our understanding of the cloud comes from theory, from models, and from the cometary ambassadors it sends. And we are reading the library through the occasional letter that arrives, not through direct access to the shelves. Consider one of the most intriguing and actively debated questions in contemporary planetary science. The possibility that the outer solar system harbours an undiscovered large planet whose gravity has been shaping the orbits of Kuiper, of Kuiper Belt and inner Oort Cloud objects. In 2016, astronomers Konstantin Batygin, Barnjari, and Mike Brown arguing that the clustering of orbital parameters among a group of distant trans-Neptunian objects, the alignment of their orbital planes and orientations in ways that appear non-random,
could be explained by the gravitational influence of a large,
undiscovered planet in the outer solar system, the proposed Planet 9, also called Planet X in some discussions, echoing the historical search for an outer planet that led to Pluto's discovery, is hypothesized to be a body several times the mass of Earth, orbiting the Sun at an enormous distance. Various estimates have placed its orbit between approximately 400 and 800 AH-UU at perihelion, with an orbital period of perhaps 10,000 to 20,000 years. If Planet 9 exists, it would be a significant resident of the inner Oort Cloud, a world that formed in the inner solar system and was scattered outward by gravitational interactions with the giant planets during the early solar system's turbulent period. Its gravity would be a significant perturbation on the inner Oort Cloud, shaping the orbits in the Hills Cloud region and potentially contributing to the delivery of some long-period comets to the inner solar system. The evidence for Planet 9 is statistical. It rests on the apparent clustering of distant object orbits, and it is debated. Some researchers argue the clustering could be a selection bias, reflecting the specific sky regions that have been surveyed rather than a genuine physical grouping. Others find the clustering compelling and are actively searching for the object itself. The Vera C, Rubin Observatory's comprehensive sky survey, should, within several years of operation, either detect Planet 9 if it exists in the predicted region, or place constraints on its properties that will resolve the question. The outer solar system continues to hold genuine surprises. As we continue our journey, let us broaden our perspective and consider a remarkable implication of the Oort Cloud's existence. The possibility that every star in the galaxy is surrounded by a similar structure. The process that formed the Oort Cloud, the gravitational scattering of icy planetesimals from the region of giant planet formation into vast distant orbits, is not specific to our solar system. It is a general consequence of the formation of massive planets in a planetary system. And we now know from decades of exoplanet research that planetary systems are ubiquitous in the galaxy. Most stars have planets. Many have giant planets. If the physics of planetary formation routinely produces Oort cloud-like structures around other stars, then the galaxy may be filled with enormous spherical halos of icy bodies surrounding the stellar populations of the Milky Way. Each star, a point of light, surrounded by a vast, cold, invisible shell of frozen worlds extending nearly halfway to the next star. And at distances where adjacent stellar Oort clouds approach each other, the outer boundaries of each extending roughly halfway to the neighboring star, the question becomes interesting. Do the Oort clouds of neighboring stars overlap? Is there material that is gravitationally ambiguous between two stellar systems, too far from either to be firmly in one system's gravitational domain? Some dynamical calculations suggest that the Oort clouds of the Sun and Proxima Centauri, currently about 4.2 light years apart, may just barely approach each other in their outer utmost regions, though the uncertainty in the cloud's extent makes this difficult to confirm. And during the Milky Way's history, the solar system has passed through denser stellar neighborhoods, has had stellar neighbors much closer than Proxima Centauri today. In epochs, the gravitational interactions between adjacent stellar Oort clouds would have been significant. Material exchanged, orbits perturbed, the cometary populations of different stars intermixed. The galaxy in this picture is not a collection of isolated stellar systems. It is a community of overlapping reservoirs. Each star clothed in its vast, icy halo, each halo brushing against its neighbours over geological timescales. Dead. Let us explore something that was theoretical until October 2017, the arrival of objects in our solar system that originated around other stars, planets. In October 2017, the Pan-STARRS telescope in Hawaii detected an unusual object moving through the inner solar system on a trajectory that was definitively hyperbolic, meaning it was not gravitationally bound to the sun. It was moving too fast, in a direction inconsistent with a solar origin, to be a comet or asteroid from our solar system. It had come from interstellar space. This object, designated 1I 217U1 and nicknamed Oumuamua, a Hawaiian term roughly meaning first distant messenger, became the first confirmed interstellar object ever detected passing through the solar system. Oumuamua was peculiar. It was elongated. Estimates of its shape suggested an aspect ratio of perhaps 5 to 10 to 1, more like a cigar or a pancake than any comet or asteroid previously observed. Showed no detectable cometary activity as it approached the sun. No coma, no tail, even though its trajectory brought it within approximately 38 million kilometers of the sun, a distance at which any icy body should have been sublimating vigorously at, and it exhibited a non-gravitational acceleration as it moved away from the sun, a small but persistent push that could not be explained by gravitational forces alone. Explanations for Oumuamua have ranged from a hydrogen iceberg, a body made of solid molecular hydrogen, too diffuse and transparent for outgassing to be visible, to a nitrogen shard from the surface of a Pluto-like exoplanet disrupted in another stellar system. One controversial proposal suggested it might be an artificial object, a light sail from another civilization. This hypothesis, proposed seriously by some researchers, is not supported by consensus in the astronomical community, but it illustrated how genuinely strange Oumuamua was. 2019, a second interstellar object, comet Borisov, was detected. This one behaving much more like a conventional comet, with a visible coma and activity, consistent with a cometary origin around another star. The detection of interstellar objects confirms that material is exchanged between stellar systems, that the contents of other stars' Oort clouds or analogous structures occasionally make their way to our solar system, and presumably our Oort cloud ejects material that travels to other systems in return. The galaxy is not merely a collection of separate systems. It is an ocean, and its objects drift and mingle over astronomical timescales. As we move toward the conclusion of our journey tonight, let us consider what may be the most profound aspect of the Oort cloud. Its role as the solar system's oldest and most complete archive, the extreme cold of Oort cloud distances, temperatures of perhaps 4 to 7 degrees Kelvin, just barely above absolute zero. Chemical reactions essentially cease. Katalov. Molecules cannot overcome the energy barriers needed to rearrange themselves into different configurations. Radioactive decay continues. but the heat it generates is immediately radiated away into the cosmic cold. Solar radiation and cosmic ray bombardment affect only the very outermost layers of surfaces, a thin rind of processed material over an unmodified interior. The result is extraordinary preservation. The icy bodies of the Oort Cloud have been sitting in cold storage for 4.5 billion years. Since the formation of the solar system, the material in their interiors has barely changed since it was assembled from the primordial solar nebula in the first few million years of the solar system's existence. When one of these bodies is eventually perturbed into the inner solar system and approaches the Sun for the first time, it is carrying pristine samples of the original material, including the Earth, including every living thing on Earth, formed. Its gases, released by sublimation, carry the isotopic signatures of the pre-solar grains from which the solar nebula was assembled. Its dust carries the organic chemistry of the interstellar medium from which the Sun formed. In some sense, every long-period comet that arrives in the inner solar system is a message from the solar system's own beginning. Time capsule, frozen 4.5 billion years ago and only now being opened. The study of cometary chemistry, particularly of the fresh first approach long-period comets that have never been processed by previous inner solar system visits, is one of the most direct windows we have into the conditions of the early solar system and the chemistry from which life on Earth ultimately arose. The Oort Cloud is not merely a reservoir of comets. It is a library, a 4.5 billion year archive of the solar system's beginnings, written in ice and preserved by the cold of interstellar space. Thus conclude the scientific portion of our exploration by returning to the scale of the Oort Cloud, but now with everything we have learned to appreciate it more fully. The solar system that most people carry in their minds is the planetary solar system, the Sun, the 8 planets, perhaps the asteroid belt and the Kuiper Belt, a structure perhaps 50 to 100 ANU across. The real solar system is the Oort Cloud. The Oort Cloud defines the solar system's true spatial extent, the region of space within which the Sun's gravity dominates over other stellar gravities, holding objects in gravitational bondage across geological timescales. That region extends to approximately 100,000 NU, approximately 1.6 light years, approximately 1/3 of the distance to the nearest star. The planets on this scale are not the solar system. They are a tiny, dense cluster at the very center of the solar system, a dot at the middle of an enormous sphere. The familiar 8 planets, together with all their moons and all the asteroids, all the Kuiper Belt objects, all the trans-Neptunian objects, all of them together occupy less than 1/1000th of 1% of the linear scale of the full solar system. The solar system is 19.99% Oort Cloud, and the Oort Cloud is populated by trillions of icy bodies, each orbiting on timescales of millions to tens of millions of years. each carrying within it preserved material from the solar system's formation, each a potential comet awaiting only the right perturbation to begin its long fall inward. The solar system is not the small planetary family we typically imagine. It is a vast, cold, ancient sphere of frozen worlds, at whose very centre, barely visible on the scale of the whole, burn the sun and its planetary companions. We are deep inside the solar system. We have barely begun to explore it. As we move into the final passages of our journey tonight, let us sit with what the scale of the Oort Cloud means, not physically, but philosophically, what it implies about our place in the cosmos and our understanding of the world we inhabit. Human beings have always had a relationship with scale. The history of astronomy is, in large part, a history of the universe growing. Not the universe itself, but the universe as understood by human beings. Each generation of astronomers has extended the known scale of things, pushing the horizon outward, forcing a renegotiation of what counts as large. The ancient cosmos had a scale of thousands of miles, the celestial sphere not far above the stars. The Copernican revolution revealed a solar system of astronomical units. The 18th and 19th centuries mapped the scale of the Milky Way in thousands of light years. The 20th century revealed the extragalactic universe, billions of galaxies across billions of light years. The Oort Cloud is, in a sense, the most intimate of these scale revisions because it concerns not the distant universe, but our own solar system. The neighborhood we think we know, the system whose planets we have visited with spacecraft, whose major bodies we have named and categorized, whose dynamics we have modeled with high precision. And yet this neighborhood extends in its full spatial reality, nearly halfway to the nearest star. It contains trillions of objects we have never seen. It connects Earth's history to galactic dynamics and to the broader community of stars through whose Oort Cloud clouds our outermost objects brush on geological timescales. The Oort Cloud tells us that even the most familiar things, the solar system, our own cosmic neighborhood, are larger, stranger, and more complex than any framework we have yet constructed to understand them. It is an invitation to humility. And in humility, there is a particular quality of wonder. Not the wonder of mastery, but the wonder of encounter, finding, in the place you thought you knew, a depth you had not imagined. And so we arrive gently and without hurry at the end of our journey tonight. We have travelled a very long way from Earth, from the familiar planetary solar system, the Sun at the centre, the planets in their neat elliptical orbits, the asteroid belt and the Kuiper Belt marking the edges of the familiar, out past Neptune and Pluto and Sedna, past the heliopause and the scattered disk through the inner hills cloud, and out into the vast, cold, dark outer Oort Cloud, where the sun is just another star and the orbital periods are measured in millions of years. We have traced the cloud's origins to the turbulent early solar system, to the gravitational chaos of planetary formation that scattered icy planetesimals outward and left them drifting in the cold. We have followed the galactic tide as it slowly talks their orbits, sending occasional ambassadors inward to the inner solar system where they blaze as comets. We have considered the comets themselves, those 4.5 billion year archives of the solar system's beginnings, carrying within their icy nuclei the preserved chemistry of the solar nebula from which everything, including us, formed. We have met Oumuamua, the first confirmed visitor from another stellar system, and had recognized in its arrival the reality that the galaxy exchanges material between galaxy exchanges between its Oort clouds, that our outer solar system is not a sealed vault, but a permeable frontier. We have sat with the remarkable fact that every star in the galaxy is likely surrounded by its own vast icy halo, and that in the regions where adjacent stars approach each other closely, those halos have brushed together, exchanging their contents, cross-pollinating the outer solar systems of the galaxy over billions of years. And we have rested with the scale, the true scale. The solar system that extends 1.6 light years in every direction. That is, by volume, more than 99% Oort Cloud. The planetary solar system we usually picture. The Sun, the 8 planets, the belt of asteroids, the disk of the Kuiper Belt is a tiny, dense nucleus at the center of something enormous, ancient, and largely unknown. Tonight, as you rest, the Oort Cloud is out there in every direction, billions of kilometers, above you, below you, to every side. Though of course those directions become meaningless at those distances, the geometry dissolving into the simple fact of omnidirectional space, trillion icy worlds, each following its long, slow orbit around a sun that appears to them from that distance as a bright star among stars. Some of them are falling inward right now, not quickly, at the orbital velocities of the outer Oort cloud. The word quickly loses its meaning, but gradually, imperceptibly, drawn by the sun's gravity and nudged by the galaxy's tidal breath, some fraction of the cloud is always drifting inward. Some of those drifting objects will, millions of years from now, reach the inner solar system and blaze as comets. Some will pass through and return to the cold. Some will be captured into the shorter orbits and become the short period comets of the future solar system. The Oort cloud is not static. It is alive as, with the slow dynamics of gravity operating on vast timescales, it is a reservoir that leaks gradually and continuously into the inner solar system, replenishing the cometary population, delivering ancient material to the planetary region, occasionally striking a planet and leaving a crater, or contributing water or organic chemistry to a world's surface. It has been doing this for 4.5 billion years. It will continue for billions more. The Oort cloud is not merely the edge of the solar system, it is the edge of home, outermost boundary of the sun's gravitational domain, beyond which lies the true interstellar medium, the space between the stars, the ocean in which every stellar island, with its planetary companions and its icy outer halo, slowly drifts. We are inside that domain. inside the sphere, within the gravitational embrace of a star that holds 1 trillion icy worlds in its outermost orbit. The solar system is not a small place. It is not the tidy, familiar, well-mapped neighborhood of the textbook diagrams. It is vast and cold and ancient and largely unknown, and filled with more worlds than we have ever counted or named or visited. Somewhere in that vastness, in the cold and dark of the outer cloud, at distances that take light over a year to cross, there drift objects that formed in the first few million years of the solar system's existence. Objects that have been waiting in cold storage through the entire history of Earth's geology, through the entire 4 billion year story of life on this planet, through all of human civilization and all of human science, waiting for the right perturbation, the right gentle nudge from a passing star, or the slow hand of the galactic tide, the beginning of the long fall inward, the beginning of the journey home, rested now, in the knowledge of how large home actually is. The Oort Cloud surrounds you in every direction at distances that humble any measurement we ordinarily use. Ancient, cold, patient, and full of frozen worlds that carry within them the very beginning of the story of which you are a part. You are not on the edge of the solar system. You are deep inside it. And the solar system is far larger, far stranger, and far more wonderful than you were ever told. Thank you for exploring with us tonight, Harmon. May your rest be as deep as the outer cloud is dark, and as patient